Thanks for the introduction. Today, I'm going to talk about dissipation engineering and in quantum many-body systems, which is a common topic of this conference. And usually we're used to thinking about unitary dynamics, which are reversible, but dissipative dynamics, which are irreversible, might exhibit qualitatively different physics. And why might we be interested in engineering different types of dissipation? One is that there may be a lot of novel physics that's interesting to look at due to this irreversibility. And the second is that for certain applications, the attractive nature of the dynamics may actually provide certain useful qualities. For example, if you're doing state preparation of a squeeze state, then you may have some robustness to errors in the initial state you prepare because your dissipation is going to take you to the same place eventually. So these are potential advantages, but the challenge is really that to engineer an arbitrary form of dissipation that you want to cook up, it can be actually quite difficult. And the model that we may want to keep in mind is something like a master equation that looks like this, or the dissipative part of a master equation, where the state of your system, given by a density matrix, evolves according to some jump operator, and we'd ideally want to engineer that as well. But especially with some spatial profile f of n minus m for the different particles in the system, right? And it would be really cool if we could really engineer what this profile looks like, and ideally the jump operator as well. So dissipation engineering has a very rich literature, much of which has been done by participants and speakers in this conference. So just kind of to quickly review some of the things that you can see, we can first look at collective dissipation, and these things, for example, as Tobias was talking about earlier today, can exhibit novel phase transitions. Really, this is something that comes from the fact that, for example, the atoms in a cavity can emit light and you won't be able to tell which atom it came from, and this can lead to novel effects. You can also get limit cycles and time crystals and oscillatory behavior, as Berislav was discussing earlier today as well. And you can also, as I mentioned, prepare squeeze states via dissipation that maybe have some advantages compared to unitary preparation. So in the opposite limit from collective dissipation, we can look at nearest neighbor dissipation, which would be the case that if, let's say I have atoms, in some optical lattice and they emit light, I can't determine which atom in a pair, actually emitted the light, and I can't distinguish this. And this has been shown by Sebastian Diehl and others to be able to create strongly correlated and topological states. You can also get non-equilibrium quantum critical points and many other effects. So the general outline of my talk will be, first, I will try to convince you that you can build some sort of dissipative dynamics with an arbitrary spatial profile, f of n minus m, which has typically not been shown in a cavity QED setup. The second is that I will try to show you that there is actually very novel physics you get from being able to control the spatial profile of the dynamics. And then lastly, I will try to tell you that there's also useful physics that you can do in a sense that you can prepare certain squeeze states that might be useful for quantum metrology. So I will, due to time constraints, give kind of a flavor of each of these, and I'm happy to go into detail more either during the Q&A or offline. So first, let's look at the experimental realization of how do you build these dissipators. So let's start with, let's say, atoms in an optical lattice. The goal of this is really to pin the atoms, and they're separated far enough apart that they're not scattering with each other, and you've turned off interactions. Then let's add a magnetic field gradient. And the real purpose of this is to add, we're going to use the internal levels of the atoms for our spin states. We're going to build an effective spin model here. And this magnetic field gradient will adjust the internal levels and give spatial addressability. So we should look at kind of the level structure we have in mind. And let's say, for example, we have these 3 levels that are relevant, right? So this S and G here would be hyperfine levels that are split by the magnetic field. And then let's say there's some highly excited state that's maybe terahertz away, very far detuned, that we can access to. Our goal will eventually be to create some sort of effective Raman transition here. So as I mentioned, this splitting between this S and G states, which we're going to use as our spin up and spin down states, will vary atom to atom on the site because of the gradient of the magnetic field. And then now let's put a cavity, what's been the subject of many of the last few talks. and a single cavity mode that's leaking out of the cavity. And this will end up mediating a dissipative interaction mechanism between the different atoms. And particularly, we'll want it to kind of enable one of the legs of this Raman transition. You can see here between G and E. We'll also add a Raman drive, which will be the last piece. But a little bit of a special thing here will be that it'll have n different sidebands. So each sideband will have a different amplitude and frequency, which nominally we can control. And we'll want as many sidebands as there are sites in the system. And the purpose of this drive is really to selectively reintroduce the interactions that we want in the system. And it'll couple essentially the other leg, this S to E leg of the Raman transition. So the one key component here is that we'll probably want to add a magnetic field offset or some other method to make the one atom transition processes off resonant. And the purpose of this is that we want the mediated interaction between pairs of atoms enabled by the cavity mode to be the dominant process. And as long as we make the single atom process off resonant, this two atom process will be the dominant one. And then by picking the sideband frequencies appropriately in line with the magnetic field gradient, we'll get the fact that this mediated interaction will only depend on the separation between atoms. And then by engineering the sideband amplitudes, it'll end up that we can actually design a particular spatial profile. So the net result will be some sort of dissipator that looks like this, where you have, a spin down flip as a jump operator with some spatial profile that you can pick and engineer one that is arbitrary, that as long as it's translationally invariant. Nominally, there'll be a coherent part to this dynamics too, which is just a mediated spin exchange. But if the cavity is sufficiently leaky compared to the other energy scales and detunings in the problem, this coherent part can be suppressed and you'll end up with just purely dissipative dynamics. These same ingredients that I've mentioned here can actually be used to engineer spatial profiles for other types of dissipation. And specifically what I mean there is other jump operators rather than just a spin flip down. It would just require probably that you pick different internal level schemes of the atoms and play certain games to get the jump operator you want. So to see that we can actually do something interesting as a result of these kind of funky non-local dissipators, let's look at the dynamics of some connected correlation function. In the top right, I've shown, let's just look at SZ. And for example, let's start with a spatial profile that's just a decaying exponential. And the intuition you want to keep in mind here is that if I look at the light that I measure leaking out of the cavity, I will only be able to tell that it came from atoms within some radius chi, which is just what sets the length scale of this exponential. And I won't be able to tell which of those atoms it came from. But if two atoms are separated by more than this distance apart, I'll actually be able to distinguish the emission came from which one. So if we plot the dynamics of the correlation function here, the x-axis here is just the site of the atoms, and the y-axis here is time expressed in units of the dissipation strength, and the intensity is just the magnitude of the correlation function. So you can see that the correlations grow initially in time and then contract back to an uncorrelated state. And I should mention that we start the system in an uncorrelated, spin coherent state. And we'd want to get some intuition for why you see this kind of contractile dynamics. And it actually turns out you can understand this from a very simple picture of just what the collective or average spin is doing. And if I look at the total spin of the system, which is just the sum of spin operators, and it will live on a Bloch sphere, right? And it starts in some coherent state, which is given by this circle here. And then as I let dynamics go on, the dissipator will start flipping spins down. And eventually it'll end up at the south pole of the Bloch sphere where all spins are pointing down. And that's another uncorrelated coherent spin state, which is what you see at late times. But along the way, it'll end up generating correlations depending on where it is on this Bloch sphere. So in the northern hemisphere, we can understand that at the very top, all spins are pointing up, and then this dissipator is going to start flipping a spin down. And as it does this, it's creating spin wave excitations essentially. But as you cross the equator, every spin you flip down will end up taking you closer and closer to the uncorrelated spin state that's all pointing down. So you're actually killing spin wave excitations in the second part of the evolution. this is the intuition behind why you see this kind of opening and closing, that as the spin, the collective spin is moving from north to south, you'll either, it actually controls whether the dissipator will create correlations or kill them. So we can do this, plot the same dynamics of this function, for example, for a power law spatial profile, and you end up seeing something very similar, except the correlations will actually spread much further in space because there's no real length scale associated with the interaction. So now we can try to use this intuition that we got, that it's really the position of the collective spin which determines and biases what the dissipator does, to add a uniform field to the system. And that's just given in the top right here. You can think of it as some constant uniform external magnetic field pointed in some direction. And so this field by itself can't actually create any correlations. There's no spatial resolution to it. In left by itself, a system evolving under this field would just rotate around whatever axis this field is pointed in. But as I mentioned, because it controls kind of the direction of the total spin, it'll end up biasing what the dissipator does, whether it creates or kills correlations. And you can exploit this fact by picking certain values of the field direction and relative strength to the dissipation to create all sorts of funky correlation patterns. And if you look at the one on the left, we can kind of control how long the correlations stay in time. This looks very similar to the previous plots I showed you, but the temporal window that you have these correlations is increased by a factor of 5, for example. The middle plot, you can show that you can also create these kind of metastable oscillations, which are reminiscent of limit cycles. Of course, with just the ingredients here, it's not some sort of stable oscillation, and it will eventually decay. But it is curious that you can see these types of oscillations, even though there's no explicit drive in the system. And then the last plot, you can see that, very similar to the usual dissipative state preparation schemes, that after some initial period of dynamics, we are actually going towards some increasingly correlated state. And we can actually, for the moment, focus on this last aspect of it and say, hey, can we understand this a little bit better, and what can come out of these types of correlated states? So this is where I'm going to talk a little bit about spin squeezing. And just let's review the usual paradigm for those who may not be familiar. If I start with a system of collective spins and their state is all, in some coherent spin state, all pointing the same direction with a well-defined phase, this spin will live on a Bloch sphere, it'll rotate around, and generically it'll have uncertainty in the perpendicular directions to the total spin that are equal to each other, given by these circles on the Bloch sphere. We can squeeze the quadratures in one direction by increasing the variance in the other, and this is called a spin squeeze state. And this is useful for metrological applications, for example, using Ramsey interferometry, where the sensitivity of the system with which you can measure some uniform external field can be related to this variance and map to the variance of the spin in one quadrature. And you can exploit this to get more precise measurements of the uniform field, the strength of the uniform field. And typically the parameter that quantifies this enhanced precision is called a squeezing parameter. And you can see that it's really just related to the variance of the spin and in the perpendicular direction on the Bloch sphere. And this really quantifies, essentially, compared to an uncorrelated system, how much entanglement can help you make more precise measurements of the uniform field. So this is the typical picture that people talk about in quantum metrology for use in sensing magnetic fields, or even for making precise atomic clocks. But we can also ask the question, well, what happens if you want to sense a spatially varying field rather than a uniform field? And naively, you can try to close your eyes and write down a spin squeezing parameter for this case, but this actually turns out to be a little bit subtle, because these Fourier components S of k of the spins, unlike the collective spin operator, which corresponds to k equals 0, don't actually live on a Bloch sphere because they don't satisfy a closed spin algebra. But nonetheless, it turns out that you can define a squeezing parameter that quantifies the enhanced precision you can get to measure a particular k component of a spatially varying field. So the picture you want to have in mind is, I have my atoms in some lattice that represent spins. I apply some spatially varying magnetic field, and my task is to precisely measure one chosen Fourier component of this field. So now let's see how we can actually do this with the dissipative dynamics I mentioned before. Let's pick a spatial profile that looks like this. It's a cosine with some k star. This wave vector is the one that we'll end up wanting to sense, multiplied by an exponential, and I'll explain in a moment why we choose this form. And then we can plot this finite wave vector squeezing parameter. And in this plot, the x-axis is time, expressed in units of the dissipation, and the y-axis is the squeezing parameter. And what we really want is the smaller the squeezing parameter is to a limit of 1 over n, where n is the number of particles in the system, the more precise we can make the measurement. And so what I've plotted is a few different lines where each line corresponds to a different wave vector. And you can see that the k star we chose, which was 0.3 pi in this case, ends up being much more squeezed than any of the other modes, including the usual collective mode that senses the uniform component of the field. And in fact, it seems almost that by squeezing this particular k mode, we are anti-squeezing some of the others. And the intuition you can get behind how are we actually able to select out one of these modes is that, at least in this model, the squeezing of a particular wave vector grows with the spin wave occupation at that wave vector. And so by picking an interaction profile whose Fourier transform, which is given in this inset here and this brown curve, is a sharply peaked Lorentzian around the wave vector we want, we can preferentially generate excitations at that wave vector during the course of dynamics, and hence increase squeezing at the particular mode we want. So this is kind of interesting that using pure, largely correlations created just by dissipation, you can selectively enhance precision to measurements at a particular wave vector of choice. So we can think now, what are perspectives to go forward along this line? On one hand, I showed you that you can select out a particular wave vector, but the actual amount of squeezing was nowhere close to the 1 over n that you'd really want. So we can try to enhance this, the actual quantitative value of this parameter by either doing something like feedback optimization, using the fact that light leaked out of the cavity, you can measure and apply as feedback basically for free. You can also imagine doing something like using ensembles of atoms at each site rather than a single one. This is similar, I think, to what Monica Schleier-Smith does at Stanford. And this also should enhance metrological sensitivity. We can also ask what interesting physics might we be able to get out of this type of non-local dissipation. And as Tobias mentioned earlier today, there's a lot of interesting dissipative phase transitions that you can study in these systems, but the dissipation there is still typically collective. And you can ask, if you play these same games with applying gradient magnetic fields and the right type of Raman drives and such, and you endow the dissipation with some spatial character, how would these phase transitions change? Would the critical points shift? Would you get something qualitatively new? It could be a very interesting direction. And the second is that, as Berislav was mentioning, actually at these phase transitions, you can get enhanced squeezing, and you can ask then, could this actually connect back to the first statement I made, that you can use this even to enhance quantitatively the value of squeezing at some wave vector. Lastly, this is more in the line of the correlation dynamics that I showed you. You can try to think about dissipative transport or entanglement spreading. There's a rich literature, like a lot of it coming from Alexei Gorshkov at UMD, about long-range growth of correlations using long-range Hamiltonians. And you can ask what happens, if anything, is different when you make these correlations generated purely by dissipation instead. Even though for long range, even defining a light cone is a bit challenging. So with that, I'd like to thank my collaborators on this work and open up for questions.